In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranab is here to deliver today's presentation, Power Transformer Part 71. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with the bubbling inception temperature would have to depend on many other factors. One, operating temperature. Two, porosity, thickness and water content in cellulosic paper insulation. Degradation of cellulosic structural integrity. 4. Presence of acids that would cause to decrease the surface tension of the oil, and that combination also leads to decrease the energy as needed to produce a bubble. 5. Moisture saturation limit of oil would have to increase with aging of cellulosic paper insulation, causing to raise the bubbling inception temperature. Number 6, transfer of water molecules from paper to oil would cause to escalate oil aging process, which may lead to decrease the bubbling inception temperature of the oil. Number 7, type as well as the basic difference in microstructure configuration of mineral oils. Number 8, thermochemical properties of the liquid dielectrics such as thermal conductivity, viscosity, heat capacity, and density. Now, moisture exposure is the most influencing factor to endanger transformer insulation system. It is rather to exhibit that there would have constant exchange of moisture between oil and solid insulation during the particular phase of temperature transients. With the increase of water content is released from cellulose insulation to oil, and the exchange process would have been revert back to cellulose from the oil when the temperature subsides or is gradually returning to normal. Only the surface moisture of cellulosic insulations would have to take part in this moisture exchange process during the variation of load cycle and temperature. Normally, water molecule at the inner layer of cellulosic insulation would remain unchanged for years together or even decades. As the water solubility of oil is temperature dependent, so assessing the oil's breakdown voltage that would always have to depend on the percentage of relative moisture saturation in oil. Relative saturation of water in oil that refers to the percentage of water dissolved in the oil compared to the maximum amount of water that can hold by the oil at a specific temperature and pressure. Relative saturation is thus to calculate by the ratio of actual water content in the oil to the maximum water content the oil can hold at that temperature, and it is expressed in units of percent. As of ASTM standard D6004-2020, Carl Fisher titration is the most accepted analytical technique that to use volumetric and colorimetric titration to determine the amount of water in oil sample. The determination of water content in oil can be measured in any state of mixing, such as dissolved, free, or emulsified, where the measurement that are being resulted in milligram per kg of oil or in percent level of concentrations. As per guidelines of the standards IEEE C57106 and IEC 60422 2013, where it is recommended to collect oil sample annually for the purpose of performing Carl Fisher titration to measure the water concentration in oil in units of milligram per kg. Concept of relative saturation of water in transformer oil as being interrelated both with solid and liquid insulation. So, excessive water content in insulation system would therefore directly affect the following state of internal characteristics of the transformer. 1. Decreases the breakdown strength of the insulation as of figure 195. Reduction of the water vapor bubble initiation temperature. Reduction of the water vapor bubble initiation temperature. Accelerates cellulose decomposition. Accelerates the aging rate of the insulating materials. Now, see the graphical interpretation. Breakdown voltage relative to dry oil and relative saturation of water in percentage. As the water content in oil would have to vary with temperature, so the relative saturation of water would also changes in response to changes in oil temperature. Temperature variation of the transformer oil in conjunction with water would thus to depend on the following conceptual aspects. 1. Mode of oil circulation and criteria of heat dissipation as employed. Geometrical configuration of core and winding arrangement. Oil flow characteristics and winding temperature distribution. Number 4, designing characteristics of electrostatic and magnetic shielding, etc. Outcome of all the above factors would have a great significance to restrict the rise of temperature and is thus to channelize the cyclic system of kinematics of water absorption or desorption by the cellulosic paper insulation. From the graphical representation as shown in figure 195, it is much indicative that if the relative saturation level is to be kept below 20%, then there would have no significant change in the dielectric breakdown voltage of the insulating fluid. But the breakdown voltage of oil starts to drop significantly just above 20%, the relative saturation level of water in transformer oil. However, the complexity in temperature-driven moisture exchange dynamics of a loaded transformer would have been made the situation rather critical to find out the active water component in oil or in cellulosic paper insulation by measuring only through a time-ridden relative saturation parameters. In combination of water, oxygen, and high temperature would always be involved in accelerating the degradation process of transformer insulation. Transformer oil oxidation is a natural process where oil reacts with oxygen and heat. Oxidized transformer oil, when it comes in contact with water molecules, then the cellulosic paper insulation would have been degraded by the process of hydrolysis. A hydrolysis mechanism is a chemical process where the cellulose's glycosidic bonds, the bonds that link glucose units together in cellulose chains, would have been attacked by the water molecules, causing the chains to break down. Rate of hydrolysis is to be escalated with the rise of temperature, as because at elevated temperature the glycosidic bonds would have been much more susceptible to attack by water molecules. Acids, which are to be formed as the byproducts of the degradation of oil or cellulose itself, would have to catalyze these hydrolysis mechanism, causing to breakdown of cellulose chains much faster. Transformer oil aging process through slow oxidation as of due to have chemical reaction of dissolved oxygen with oil molecules, especially at higher temperatures, cannot be fully restricted even with best efforts to deploy. This oxidation process leads to the formation of various species of oxygenated byproducts, including carbon dioxide and low molecular weight carboxylic acids. These carboxylic acids are indeed hydrophilic in nature, as because they have endowed with a polar carbonyl group, that is COOH, which makes them water soluble and hydrophilic. Both water and carboxylic acids, as formed during the oil degradation process, are of the polar molecules. It is as because both would have an uneven distribution of electrical charge, with a partial positive charge on one end and a partial negative charge on the other. The degradation process is cellulosic paper insulation. Degradation as due to certain chemical reactions. These reactions through pyrolysis, hydrolysis, and oxidation. These three processes. The pyrolysis is the process of chemical decomposition which would have to be brought about by high temperatures. One of the processes of pyrolysis is thermolysis, which refers to the thermal decomposition of organic materials like cellulosic paper insulation in absence of oxygen. Most important. Hydrolysis. Hydrolysis is the chemical breakdown due to reaction with water. Such reaction will cause depolymerization of cellulose chains and decrease the tensile strength of the paper, reducing the mechanical stability of the cellulosic insulation system. And the third one, oxidation, is the process through which there is loss of electrons, gain of oxygen, or loss of hydrogen. Oxidation of cellulose insulation would have to degrade its physical properties, leading to a reduction in insulation strength. Now discuss regarding pyrolysis. Pyrolytic degradation or thermokinetic degradation of cellulose-based insulation in transformers can be categorized by the nature of breakdown of cellulose insulation due to have an aggressive heat as generated by the load current or fault current without the influence of water, oxidation or other agents. Breakdown phenomenon of cellulose molecules through pyrolytic degradation would have significantly accelerated at elevated temperatures, typically above the temperature of 300 degrees centigrade. Pyrolysis reaction actively is also being the resultant effect of producing high amount of energy deliberated from arcing within the transformer. During pyrolysis, the cellulose molecules is first to decompose and there would have an easy breakdown of the bonds between atoms into smaller fragments of the C and H, C and O, or CC. At the intermediate stage, where temperature would be at greater than or equal to 120 degrees centigrade, levoglucosan, that is C6H10OS, a major byproduct of cellulose pyrolysis, would have been formed. However, the cellulose, a key component of plant fibers used as in transformer insulation, is a linear polymer of glucose molecules linked by C1-C4 glycosidic bonds. The chain structure that would have become more stable when the strong hydrogen bonds connect with these glycosidic linkages. The average length of cellulose polymer chain is referred to as the degree of polymerization, and it is to be measured by the average number of glucose monomers linked together in a polymer chain. In pyrolysis reaction, heat is therefore be the major parameter that would affect the mechanical strength of cellulose by breaking its glycosidic bonds. From analysis, it has been observed that decomposition of cellulose insulation would thus to begin at temperature of 250 to 260 degrees centigrade, and at that phase, only the dehydration of cellulose has been observed. During pyrolysis reaction at temperatures of about 300 to 350 degrees centigrade, transformer cellulose insulation would have to undergo a process of thermal decomposition that breaks down the cellulose into smaller molecules, releasing significant amount of water and other volatile byproducts such as methanol and ethanol. It is obvious that such phenomenon of severe temperature rise would only have been caused during certain incidents of an electrical fault or short circuit. Cellulosic component is a type of complex carbohydrate and is basically composed of many glucose molecules linked together. The water molecules released in the course of pyrolysis reaction does not only accelerate hydrolysis of carbohydrate, but it directly deteriorates the insulation properties of the system. Hydrolysis. In transformer, hydrolysis is the process by which there would have a chemical breakdown of the existing cellulose polymer chains within the insulation paper due to reaction with water. Fundamental and the most crucial property of cellulose insulating paper would have to depend on its tensile strength. Tensile strength measured in megapascal, that is MPa, would thus to indicate the maximum stress a material can withstand when pulled or stressed before it fractures or breaks. Material with having higher MPa value that represents its greater resistance to tensile forces per unit area. As per recommendation of IEC 60641-3-2 standard, the tensile strength of kraft paper for applications like power transformers should have to be greater than or equal to 75 megapascals. However, the tensile strength is directly proportional to the length of the cellulose chain. Again, I repeat, the tensile strength is directly proportional to the length of the cellulose chain. Hydrolysis reaction between water and cellulose that has to initiate at the basic temperature level of 70 degrees centigrade to 130 degrees centigrade. The cellulose chain length would have become shorter as with the presence of water molecules. Since the cellulose is composed of polar glucose rings that can dissolve in high quantities of water via hydrolysis reaction. Water is a good solvent due to its polarity and its molecular shape that has allowed for this polarity. Cellulose polymer of water, cellulose polymer and water, both are comprised of polar molecules. It is important to note that cellulose has always had a strong affinity to itself and any of the materials containing hydroxyl functional groups, especially water. The cellulose has a crystalline structure with the highest content of hydroxyl functional groups. Specifically, these hydroxyl groups would have a crucial role in cellulose's properties, such as its ability to form hydrogen bonds and its reactivity. Hydroxyl groups which can form hydrogen bonds because of the electronegativity difference between oxygen and hydrogen, making the oxyhydrogen bond polar. Once the cellulose chains come in contact with water media, then there may have immediately to form larger amount of hydrogen bonds. As being greater in number of hydrogen bonds, the cellulose chains would have promptly interacted with the water molecules. Therefore, cellulose chains that are to be encircled by several numbers of water molecules as because the partial negative charge of the dipole of water molecules would have been attracted by the positive charge of the cellulose chains and vice versa. In hydrolysis reaction, water is the primary component whose molecules would have to accumulate between the cellulose chains, causing to initiate the process of thermohydrolytic degradation within the cellulose chains. Thermohydrolytic degradation process would have to undergo due to the combined effects of heat and moisture, causing a subsequent breakdown of cellulose chains. The thermokinetic degradation of cellulose would specifically be a complex process of pyrolysis or thermohydrolytic reactions involving multiple stage of thermal decomposition of cellulose subject to variation of heat. Hydrolysis reaction will cause depolymerization of cellulose chains, which then to involve in breaking down the long cellulose chains into smaller glucose units through the addition of water molecules. Cellulose is a linear polymer and is to be constituted with a large amount of molecule formed by linking many monomers together. Monomers are the small molecules that can have the ability to chemically bond with other similar molecules, creating larger and more complex molecules. Such bonding process of monomers is referred as the process of polymerization to create polymers. In case of cellulose, whose monomeric unit is glucose, and there would have a formation of long chains of cellulosic structure when these glucose molecules that are to be linked together by glycosidic bonds. Now let's see the thermal stages of cellulose decomposition in power transformers. First stage, degradation in the range of the temperature 70 degrees centigrade to 130 degrees centigrade. That is, physically absorbed water molecules in cellulose would start releasing at temperature of 120 degrees centigrade. However, prolonged thermal degradation process would thereby start to initiate at relatively low temperatures, that is around 70 degrees centigrade to 80 degrees centigrade. Again, I repeat, first stage of degradation in the range of temperature 70 degrees centigrade to 130 degrees centigrade. Actually, physically absorbed water molecule in cellulose would start releasing at temperature of 120 degrees centigrade. However, prolonged thermal degradation process would thereby start to initiate at relatively low temperatures, that is around 70 degrees centigrade to 80 degrees centigrade. Now, second stage of degradation at temperature range 250 degrees centigrade to 360 degrees centigrade. Thermal decomposition of cellulose will start to begin at temperature of 250 degrees centigrade to 260 degrees centigrade. Thermal decomposition of cellulose will start to begin at temperature 250 degrees centigrade to 260 degrees centigrade. At about 360 degrees centigrade, there would have abrupt stage of dehydration and decarboxylation reactions which produce combustible gases like aldehydes, ketones, ethers, etc. Third stage, degradation at temperature greater than or equal to 400 degrees centigrade. Temperature range from 300 degrees centigrade to 550 degrees centigrade is to be identified as the pyrolysis zone of the cellulose, and the maximum weight loss at the temperature interval is 450 degrees centigrade to 500 degrees centigrade, producing several types of volatile products. Let's stop here, further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.